Okay, so welcome to module 10, lecture 2 and 3. So this is on scan chain based sequential circuit testing. So if you remember in the last lecture, that is lecture 1 of module 10. So what we have discussed? We discussed that a sequential circuit testing as compared to a combinational circuit testing using the D algorithm or sensitize, propagate and justify approach. So what we had seen that in case of combinational circuit you sensitize, propagate and justify. So one pattern is enough to detect a fault, but in case of sequential circuits what we have seen that the basic architecture of a sequential circuit, you have some primary inputs and there is a state register and there is some feedback from that, and actually this is called the secondary inputs or virtual primary inputs. So as this set of inputs are non directly controllable because they are output of the state registers, so you cannot have a single test pattern to test the circuit because you require multiple number of test patterns. To be precise, if the sequential depth of the number of flip flops in a circuit is d-sequence, then you require d-sequence number of test patterns to control, in the worst case, to control all the secondary inputs. Now, once they are controllable, then you can apply the primary inputs and test your circuit. Similarly, this output of this is also not directly observable. So, to make it observable directly, so you have to again propagate the value through some of the flip flops, which take another set of time. So, so single test pattern we have already seen is not enough to test a sequential circuit by sensitize, propagate and justify approach. So, first you have to use d-sequence level of number of test patterns to control the secondary inputs, then apply the primary inputs. So, d-sequential number of patterns plus one pattern, and again also you have to output the propagate the value of these outputs to observe them. So, more than one number, that is d sequence plus 1 or some plus k number of test patterns are required to test a sequential circuit. So, and also you know that whenever we are going for what you called this ATPG based testing with sensitize, propagate and justify approach, at many times you can lead to inconsistency. So, leading to inconsistency, again you have to backtrack. So, you can assume that sequential circuit testing is order of complexity of combinational circuit testing into number of test patterns to be applied. So, if you can think that we have also discussed on the time frame expansion method, that if there are d sequence number of depth of the sequential flip flops, then you may require to go to minus d sequence to 0 level of time frames, that is d sequence number plus 1 time frames are required to do this. So, you can understand that in the last time frame, so every step was successful, but in the last time frame if you lead to inconsistency, then whole work is gone and then again you have to start with afresh. So, because of this inconsistency, today we will see what we can do so that this overall complexity of the more than one number of test patterns can be avoided or can be minimized in sequential circuit testing. So, effectively what you have to do? So, effectively you have to somehow indirectly or directly control and observe the secondary inputs and secondary outputs respectively. If you can do that, then our problem is solved. So, let us see what we will do. So, as in the introduction we are discussing, the major problem of testing of sequential circuit is difficulty in controlling secondary inputs and difficulty in observing secondary outputs. So, somehow we have to do that explicitly or using some other circuitry which is called design for testability or some other arrangements we have to do this. So, that is why we require a sequence of test patterns for ATPG of sequential circuit, which you want to make it to one kind of a thing. So, in this lecture what we will do, we will see what we can do in the circuit level, so that ATPG for combinational circuits would suffice for sequential circuit. That is, somehow we have to use ATPG algorithm, D algorithm for combinational circuits and do that and say that it is done for sequential circuit, and the parts which you have to control indirectly, we will use some other technique which is actually called the scan chain, as you will see, to control them indirectly. Okay, and this is one example of a scan chain design where in VLSI we call quote unquote simple designs are great. So, if you are doing a very complex design with lot of flip flops, lot of gates and all, there is a very high chance that your design is improper or inefficient. But good designs are always simple. That is a quote unquote thumb rule in VLSI. That if your design is very simple and you have solved the problem, then you are the greatest engineer. So, great designs are always simple. So, you will find out that how this nightmare problem of testing one fault you require d-sequence number of patterns to test a sequential circuit was solved by a person who developed scan chain, and his design was extremely simple. So, this is one proof that you can do very elegant design simply. So, and actually he converted all these sequential circuit to combinational circuits, and then combinational circuit ATPG algorithm suffice for everything, and then so slowly we could do away with the sequential test pattern generation with time frames and all. So, they lost their importance, and combinational ATPG with design for testability is modifying the circuit so that you can directly control the secondary inputs and secondary outputs observability indirectly using some kind of extra circuit then came into picture. So, but for that, to achieve that, you have to put some extra circuit on the chip which is called DFT. So, that will be an extra overhead. Okay, but anyway, that extra overhead problem is not much, as we will see, then compared to the offline headache of for one fault generating this sequence number of test patterns. So, how to do that? So, one major problem we have seen in the last lecture was to control the output of the flip flops which are nothing but your secondary inputs. So, how can you do that? So, one very simple way of, as we already discussed that in our lectures, we will be using D flip flops as they are standard used in all VLSI circuits. So, one way how can you indirectly, that is you have to indirectly or directly, whatever you can say, without using explicit test patterns, directly you have to get access to these flip flops somehow and you have to control them. So, indirectly if you want to control them, I mean you can apply D sequence number of test patterns and go for a time frame expansion and you can do it. But here what we are saying that this indirect control, we have to do it somehow directly. We have to directly somehow access all the flip flops and do this. So, you can understand that if we can somehow get hold of the set and reset pins of the flip flops, then you can always what you can call take control of the flip flops. We will see examples. If you can directly somehow get access to the set and reset inputs of the flip flops, then you can directly say make them 0 or 1 as required for the secondary input. So, at that time you did not go for this D sequence number of test patterns to make these secondary inputs controllable indirectly. So, we can use that. So, what is this truth table of the D flip flop you can say? So, if I make you say reset equal to 0 if you say, then your and set equal to 1 if you say, then you are going to set your flip flop. So, what is the idea? Input you do not care at that time because you are directly controlling the flip flop using set and reset, and clock is also you do not require, you will directly get the output Q as 1. Now, if you make the reset as 1 and set as 0, then what is going to happen? You will directly get the output of the flip flop as 0. You did not apply clock and all those things. So, somehow if you can control the set and reset lines externally, then you can directly set the secondary inputs as you require. Okay, and 1 for the set and reset is not allowed because it is a illegal condition. But now, if you want to operate normally on your flip flop, then you make set reset equal to 0, this one, and if you apply a 1, if you apply a 1 when you set and reset a 0, you apply a clock edge, in the next edge you will get a 1, because D flip flop you apply a 1, then you apply a clock edge, your set and reset should be 0 at that time, in the next clock edge you will get a 1, and 0 for the same case. If you give input as a 0 and then apply a clock pulse, your set and reset should be 0, the output will be a 0. So, the normal operation of a flip flop. But if you want to directly, if you want to use the clock pulse to control this flip flops, then you know that this input there will be lot of combinational clouds, there will be another set of flip flops over here. So, you require the sequence number of test patterns to set this input so that you get the desired output at this one. So, if you want to get a 0 over here, indirectly you have to set a 0 over here, for that you may have to control this flip flop and so forth. So, for which you require the sequence number of patterns. Okay, now, if you somehow control this and this, then directly you make reset equal to 1 and set equal to 1, you do not even need to apply a clock pulse and you will get the output as 0, which is required. So, let us see what you gain by this. You can directly do this. So, if you remember in the last lecture, we said that this was a circuit. You can think that the set and reset lines were not there. So, the idea was that we are asking, can you test this fault? Then we find out that if the set and reset lines are not there, it was in the question and answer section of the last lecture, then we found that this fault cannot be tested because you know that this output is x, this output is x, kind of a thing, and for this stacked one you have to apply a 0. And if you know that this is 0/1, and in the case of XOR gate, this output will be x or x prime, because x 0 in case of XOR gate, the output is whatever is the input here, that will be the output, and if you apply a 1 over this for the case of fault, this x will become x prime. So, it will be x and x prime. So, never you can get any concrete value and you cannot ever test your circuit. So, that was the case. Now, we can see that use of the set and reset lines if you have, then what can you do? So, for example, we know that all the lines are x for the time being. So, this is x, this is x, this is x and so forth. So, what do we do? So, what I can do is that now we have a direct access to this flip flop. So, you make set equal to 1 and reset equal to 0. So, what you do once you do that, so without applying the clock also, this output will be a 1. So, this output is 1 and this output is a 1, because we have set the flip flop directly. Okay, using set and reset. Now, this is stuck at 1. So, what you can do is that, so you have a 1 over here, you have a 1 over here. So, And now, so this you got just by what you do, the first step what you have done, first step you apply set equal to 1, reset equal to 0, so you get a 1 over here, you get a 1 over here. Now what you do, you make set and reset equal to 0 now. So what will happen now? So now this D flip flop will be operating in the normal clocked mode. So now it is a 1 over here. So what you have to do, you can apply primary input 0, so normal case 0, fault case 1 because the stack at fault. So it is a D prime over there, and we know that in case of XOR gate, if the other input is 1, then the second input is primed, is inverted, so you get a D over here. Now what you have to do, so the set and reset you have made 0, now what you can apply is you apply a clock pulse over here. So this output will come out as the primary output which we will get here, and the fault is tested at the primary output. So what we have seen that the fault which was non-testable in the first go without the set and reset lines now become testable when you are using a set and a reset line. So this solves a great deal of problem, that some of the faults which are untestable, if you consider your circuit without the flip flops, without the set and reset line, now become testable. Secondly, one more thing is that so that again we will see in the other example. So what are the advantages of controllability and observability of flip flops with what do you call this set and reset lines? A fault which was untestable by the time frame expansion method last lecture is now becoming testable using the set reset flip flop, that is one. Secondly, so what we have seen is that now only one pattern, as we will see, only one pattern is required to set and reset the flip flops and propagate the effect to the output. So the idea is there, if you look at it, so only one pattern, that is actually you can call this set equal to 1 and reset equal to 0, that is one pattern which will set the flip flops, because if there are more number of flip flops, for all of them you have to do the set and reset as required, and there only one pattern will drive your answer to this one. So indirectly what you are going to have, if you have set and reset lines in your flip flops, one pattern will be required to set and reset the flip flop as required for your secondary inputs and secondary output kind of a thing. Secondary input controllability you can directly get by setting and resetting the flip flops directly by the set reset pins, and now one pattern is required to be applied which will sensitize the fault and propagate the value to the output of some flip flop kind of a thing. So now instead of D sequence patterns to initialize the flip flops, you can have so unlike time frame expansion where you require D sequence minus 1 patterns required to what you call sensitize, propagate and justify. So in this case only one pattern is solving the problem, or you can call only two basically, one to set the reset of the flip flops and one to actually sensitize the fault effect, that is by the combinational test pattern algorithm. That is this pattern actually, this is you are applying a 1 0 over here. So this pattern is by a combinational ATPG, and the other set reset you are doing by this one. This set you are making as 1 and 0, this is the other test pattern. So two patterns are required to solve your problem. So this actually says the number of test patterns and also the test time. So what we have done by using the set and reset lines, we have solved one nightmare problem. We are actually going towards combinational algorithms to test sequential circuit. So now instead of using D sequence plus 1 or order of D sequence number of test patterns to set the secondary inputs, and then what we are doing, then again we are coming back to this applying the D algorithm final pattern to do it. So now we are controlling, now instead of using the order of D sequence number of test patterns, what we are doing here now we are directly controlling the flip flop outputs, that is the secondary inputs, secondary outputs, by directly setting or resetting the flip flop reset and set lines of the flip flops. Now you can directly give the pattern required to test the fault. So we have drastically changed the order to 2 from the order D sequence plus 1 to order of 2. So this is a very great help, and slowly we are moving to our aim that we are converting our sequential circuit to a virtual combinational circuit for testing and applying combinational test pattern generation algorithm like D algorithm and solving the problem. Now that was a simple example, last example. So now we will go back to the big example which we have considered in the last lecture. So if you remember, this was our circuit, this was our fault, and there were two flip flops. So if you remember, so when we have done the D algorithm on that, so we have found out that we require a 1 over here, also we require a 1 over here to test the fault, because 0, so you require a 1 over here, and also you require a 1 over here. So if you apply 1 here, so you will get a 0 over here. So the effect is D over here, and this effect will be D over here. So make a 1, you require a 1 over here. So this was a 1 over here, something like this, and this was the scenario. If you look by the last lecture, you will understand. Now the main issue was here that we have, how can we, in this was a secondary input as well as this was actually another secondary input. Okay, so because this is the output of the flip flops. So somehow how can we indirectly control this? So in this case, in the last lecture you have seen that we apply a 1, applied a clock pulse, then the value came over here. After that we applied a 1 over here, and this one was already there. We applied another clock pulse, the 1 came here, and again this for the same thing, this 1 was retained. So because this 1 again has to be transferred over here. So all this we have discussed, but we require two patterns to set and do this, arrange to get a 1 and a 1 over here. We require two test patterns. First it was a 1 over here, C equal to 1 was here, So, if you see C equal to 1 was required and a clock pulse, then B equal to 1 and C equal to 1 we required to set this flip flop, sorry, this flip flop output, and then finally A equal to 1 and B equal to 1 we applied to test this fault. So, 3 patterns were required to test the fault, and this sequence of the circuit was 2, that already we have seen. Now, let us see how can we reduce this using the set and reset line of the flip flop. So, now you know that we require a 1 over here, we require a 1 over here. So, now instead of going for a time frame and actually doing clock pulse, what we will do, we will make this one as 1 and this one as 0. So, immediately you do that, you get the output as 1 because it will set the flip flop. For the same thing for the other flip flop also, you make set equal to 1 and reset equal to 0. Immediately you get a 1. So, now your job is done. So, you get a 1 over here and a 1 over here. So, what you are doing, only 2 patterns are required to do this. One pattern to set the flip flops and another pattern to test it. So, you make this and this. So, this output and this one are set. Now, what you do? So, you know that you get a 1 and a 1 by resetting this. Now, you have to again go for the normal operation of the flip flops. So, you make them 0 and 0. So, that the normal operation is done. Now, you make A equal to 1, B equal to 1. So, if you do that, so you will get a 1 over here and this will be a 0 over here. So, this will be 0, this will be 1, this is a 1 over here and a 1 over here for the AND gate. So, you get a 1, you get a D as shown, you get a D here, so you get a 0 and your job is done. So, you require 2 test patterns. One is to set these flip flops, this guy and this guy, these are the 2 guys. A, B, X are not, A, B, C are not really important. So, you set these 2 flip flops, then in the next pattern you just apply these patterns and your job is done. So, you have to remember that if you even have 10,000 flip flops, only 2 patterns are required to solve the problem. One pattern will be to set and reset the flip flops, the other pattern will be for what? The other pattern will be just if you can see, even if you have another 10 flip flops, you have to just think over that. If you have another 10 set of flip flops, then also you need not worry. Why you need not worry? Because in case of time frame expansion method, what was happening? If you have something, let us again see back what we are doing. So, if you have to observe that this, so you can think that it is a small circuit, so only 2 flip flops, so here you require 2 patterns, but the idea is not that. The idea is that even if you have 10,000 flip flops, again 2 patterns is required to solve the problem. Say for example, you have some 10,000 flip flops, some other stuff is there and so forth dot dot dot. So, if you are using time frame expansion method, then one pattern will be required to set this, another pattern will be required to set this, another pattern will be required to set this and so forth. So, if you have 10,000 flip flops in sequence, so if your D sequence is equal to 10,000, then you are in a big problem. So, if you have a 10,000 flip flops in this sequence, so you require 10,000 patterns to solve the problem. So, set the primary outputs of this flip flop, primary output of the flip flops are nothing but they are your secondary inputs. So, you have to do that and then one pattern will be applied here to test the circuit. But now, you see if you are having direct access to the set and reset lines, then what you can do? One pattern, if you want a 1 over here, you make set equal to 1, reset 0. If you want to get a 0 over here, make set equal to 0 and reset equal to 1. And similarly, if you want to again get a 0 over here, make reset equal to, set equal to 0 and reset equal to 1 and all these things you want to have, you can apply parallelly because all the flip flops are individually controllable, that you have to assume, and then your problem is solved. So, 2 patterns are done for this one. Now, you see what you gain and what you lose. So, gain is only 2 patterns to test the circuit. If as many number of flip flops are there, whatever may be the sequential depth, you need not worry at all. Your job is done, only 2 patterns are required for this one. But, so most important point is irrespective of the value of D sequence, only 2 patterns are required to test a sequential circuit. So, that is the greatest boon you are getting, that you have converted a circuit from a sequential circuit to a virtual combinational circuit and you are solving your problem. So, D algorithm is doing everything for you, you need not go for time frame expansion and all this. But, if you look at this block diagram of this circuit, this circuit is there. So, we are just looking at the block diagram. So, these are A, B, C were the primary inputs, primary output is there and 2 set lines for 2 flip flops and 2 reset lines for 2 and a clock. So, now if you think that I have 10,000 flip flops, so what will be the case? This will be the primary inputs, this is your output and this will be your clock, and how many set lines will be there? 10,000 set lines will be there for 10,000 flip flops and 10,000 reset lines will be there for the 10,000 flip flops. These are set lines and these are the reset lines. So, now you can see the complexity. So, 10,000 set lines and 10,000 reset lines are there to do your problem. And you can understand that maximum number of outputs of primary input output of a chip can be maximum 1024 or something like that, 512, but they are very expensive to get a package like this where you can have 512 for 1024 inputs. Now, if you have 20,000 inputs, such packages are not available and you cannot do a circuit like this. So, we have gone one step, that we have converted a circuit to a virtual combinational circuit and we have solved the problem, but now the nightmare have again started, that these 2 set and reset lines are too many in number. So, how can we do that? Then the engineer started solving the problem that we cannot have, we will use the concept of having a set line and a reset line and we will control them, but how can you control them by bringing them so many pinouts? So, bringing so many pinouts is not feasible because you do not have package or packages means I think you have seen the second year classes, you have seen the ICs of the digital lab, the black packages are there, this is called the DIP dual inline package. So, there are silver pins and all. So, how many you have seen? We have seen around 14, 24, maybe some 30 or 40 you might have seen for microprocessor kits and all, but 10,000 or 20,000 pinouts is almost impossible and it is not doable at all. And also that is and also you require an ATE. So, we have also discussed about ATE in the very first lecture of this testing module. So, you have to require 10,000 plus 20,000 pinouts of the ATE, which is also a very expensive equipment, and that the number of probes to give inputs to the 20,000 pins is also not feasible. So, that idea is dropped. So, now what people have done, they are saying that ATP is set and reset by shift registers. Now, the problem they have found out was, you in the same example we are going to check. So, you required a 1 over here and you required a 1 over here, that was the requirement. So, for that you have to make set equal to 1, reset equal to 0, set equal to 1 and reset equal to 0, that was the requirement if you remember. Now, what problem we had? The problem is that if you want to bring this pin, this pin, this pin, this for 4 pins. So, 10,000 flop means 20,000 pinouts will be there. Now, how to do this? So, people have said that we cannot have that many pinouts. So, how can you solve the problem? Some people give the idea that you use what is called a shift register based technique. Now, what is a shift register based technique? So, in this case we just want to minimize the pinout. So, you will have a set of what do you call and the set of registers and the set of flip flops which is in a connected in a what do you call a shift register kind of thing. So, 1, 2, 3, 4. So, there are 4 pinouts. So, you have if there are n flip flops, so you require 2n number of scan or what you can call shift registers, 2n flops in shift register. This is the idea. So, 4, so here will be 4, if there are 8 flip flops, so there will be 16 in this case, okay. So, that is the idea. Now, what you do? So, that is a problem you are having. So, now what they have done, they are saying that now instead of bringing these pinouts, they will be connected this to the output of each pin of a shift register. So, now you see, so you have 2 flip flops, I will put a shift register of 4 flip flops. So, if there are 4 flip flops in the main circuit, I will have 8. Okay, so, now the first output of the flip flop for this shift register will be connected to the set line. The second flip flop output will be connected to the reset line. Similarly, the third output of the shift register will be connected to the set line of the second flip flop, and last flip flop output will be connected to the input of the reset input of this second flip flop. So, now what you do? So, sorry. Now, what you record, the connection is done. Now, you need a 1 over here, a 0 over here, a 1 over here and a 0 over here, sorry, a 0 over here. So, now what you have to do? You can say that that is what. So, this you require a 1 at the output here, 1 0 here, 1 here, 0 here, because now this input and set and reset lines you are not driving externally from anything. Okay, so, you are not driving by pins. So, if you look at the last lecture, last slide if you see. So, there were external pins, these were external pins and you could apply them parallelly. That is, in one go you can apply all these flip flops in one go, but for that you can set and reset the flip flops, but for that what you require? You require the circuit or this chip design or the chip packaging to have 20,000 input output lines. So, that is input lines 20,000, that is extremely difficult problem, but in one go you could have controlled all the flip flops outputs directly in one parallel go. But now, in this case you require 1 0 1 0. Now, if you know that in shift register in one go you cannot have 1 0 1 0, you cannot have directly. In one shot you cannot have it. So, what you have to do? You have to apply 1, then apply a clock pulse, then 0, then apply a clock. Let us see how it will happen. So, you require 4 iterations to do this. So, first you apply a 0 over here. So, this is the requirement. So, don't go about this. So, this is the requirement you can think, this will require in the end. So, first you apply a 0, give a clock pulse. So, this 0 will come over here, correct. Now, you apply a 1 over here, 1 over here, yeah. Now, you apply a 1 over here. You apply a 1 over here and you have to remember that all these clocks are same and these clocks are different. It is very important to know this is the circuit clock and this is the shift register clock. So, 2 clocks are now coming into picture. Now, you give a 0, now you give a 1, another clock pulse you apply to all this. So, now this 0 will be coming over here. So, we will get a 0 over here and this one will be here. So, now you get a 1 over here and a 0 over here. These are all actually don't cares now. You do not know what is there because you have not fed it. Now, you give another 0 over here and give a clock pulse, sorry. you give another clock pulse over here. So, now if you give a clock pulse, what is going to happen? This 0 will be here. So, this will be a 0 over here, and this 1 will come over here, this 1 will come over here, and this 0 will go over here. So, this will be the case. And now in the end you apply a 1 here and give a clock pulse. So, once you do that, so this 0 will come here, this 1 will be coming here, this 0 will be coming over here, and this 1 will be coming over here. So, now you have 1 0 1 0 which was required. So, you require 0 clock pulse, 1 clock pulse, 0 clock pulse, 1 clock pulse. So, 4 clock pulses are required in this case to shift your value required to control the input and the set and reset input of the flip flops. Now, you can say that, so if you have say 10,000 flip flops, now what is the case? You require 20,000 clock pulses to control this flip flop. The answer is correct, that you have to do. And also you have seen that your ATE time is very expensive. You cannot have a this kind of 20,000 input time you cannot have, or it is very restrictive to do it. But now this problem, they have found out that this problem still remains. If you look at the sequential circuit testing, this problem people have not been yet to solve as of now, to minimize the test this number of clock patterns to test the fault. Somehow they are using fault collapsing, because we have already seen that fault collapsing algorithms, they minimize the number of faults. Only those things they will be doing to minimize the number of faults. But this filling up the shift register, we will see the scan chain is a modified version of this that we will be seeing in the next few slides. But anyway, this 20,000 number of patterns or whatever to set these flips reset and reset lines indirectly, or means what you can call in a implicit manner, cannot be done away with. So, this number of test patterns, the clock periods will be required to shift the pattern here, which can indirectly directly get access to set and reset line and control the output of the flip flops. But here is a problem, here is a one advantage which is solving the problem. So, this is the clock for the circuit and this is the clock for this S clock is the clock for this shift register. So, now these two clocks are kept different. Now, why is it? The idea here is that if you look at this clock pulse, so this clock pulse is driving one AND gate, and this again the output is driving another what you call inverter, then another gate. So, whenever you get the data, whenever this clock pulse comes, the data comes over here. So, the application of the clock pulse, the data will come here, then it will take some time for the value to be propagated over here. So, you cannot have a very fast clock over this period, because whenever you apply the clock pulse, your data will come here. Then to get the data here, maybe we can assume there is another flip flop over here. So, then this data, the change in data should be arriving over here, then only you can use another clock to trigger this flip flop, this DQ say. Okay, so, but this is a long path, so this output will be there, then this AND gate is there, then this inverter is there, then the OR gate is there, then the data will come. So, there will be some delay of the data travelling from here to another flip flop input. So, this clock period has a limitation in speed. You cannot go for a very high speed clock over here. Okay, so you have to use a slow clock. But if you use the shift register, so this output is connected here, this output is connected to the input and so forth. There is no gates here, no gates here and no gate here. Directly you can feed it. So, there is no delay. So, once you apply the clock comes and the result data comes here, and immediately data gets transferred to this input of the flip flop. Because had there been a lot of combinational cloud over here, then you would have to wait from this data to be coming from here to here, then only you can apply another clock pulse. But now this is not the case here. The output is directly connected from this to this, the output is directly connected from this to this. So, your problem is solved. So, you can apply a very fast clock over here compared to this clock, so that this filling up can be done in a very fast rate. So, even you have to say for 10,000 flip flops, even if you have to have 20,000 patterns to set or reset these lines, but then again your problem is not high, because if it is say in 10 megahertz clock, so you can use it at 500 megahertz clock or something like that. So, generally you can also use a gigahertz clock over here and very quickly shift the data, but this will be slow because there is a lot of combinational delay in this case. So, the number of test patterns is in this case the number of test patterns were 2, because in one pattern you set and reset all the flip flops in one go and then you apply the pattern and done it. But in this case the set reset lines have to be filled up in a sequential manner. So, number of test patterns required you can see is that 0 1 0 clock 1 clock 0 clock 0 0 clock 1 clock. That will take around 20,000 cycles if there are 10,000 flip flops, but that can be done in a very fast rate. That can be done in a very fast rate this way. And one more point you have to remember over this, that so you can ask me the question that, so 20,000 clock periods, 20,000 patterns are required, 20,000 or 2n number of flip flops patterns clock periods are required to shift the data here. So, you can say that if there are n flip flops, then 2n patterns are required to do this, to control this set and reset and do this. So, you can also say that in time frame expansion method also, we are also almost having the same thing. So, yeah, I mean in one pattern, if there is a D sequence number of flip flops, then what you have to do? You have to apply in time frame 1 you set some of the flip flops, in time frame 2 you set some of the flip flops dot dot dot, in the D sequence time frame, after D sequence time frame all the flip flops are set and you apply this. And you know that D sequence of the number, if there are n flip flops, so here 2n patterns, I mean 2n series are required, but in case of time frame expansion method only D sequence number of patterns are required, because, and you know that the D sequence is value D sequence is the value D sequence will be less than equal to n. Why? Because if all the flip flops are tied out in one chain, like in this case 1, 2, 3, 4, all the flip flops are tied out in one chain. So, here D sequence will be 4, but sometimes it may happen that there are many of the flip flops are in parallel, that is not all the flip flops are dependent on the previous one. So, your D sequence is the maximum depth of the flip flops, so that will be equal to or less than n. So, you can say that these what you call this time frame expansion methods, in each time frame you control some of the flip flop output. So, it may not be 2n, 2n is actually double the number of flip flops. Okay, so, that which is required in case of shift register based testing using set reset. Then still why you are going for this one? Why we are not going for this one you can call sequential time frame expansion method? The answer to this sequential time frame expansion method is a very complex stuff. So, what may happen is that in one time frame say DC minus D sequence you set some of the flip flops, done. In time frame D sequence minus 1 plus 1 you set some of the flip flops, but you are not using the set and reset lines to do that. So, what you are going to, how you are setting up or resetting the flip flops in case of this means time frame expansion method, you are using the primary inputs only to do that. So, primary input means you have to get access to these flip flops, you have to cover some of the combinational circuit, like for example you are saying that, so this is a flip flop which has to be controlled and there is a lot of combinational circuit over here. So, you have to control these inputs in time frames approach to get an access to this one. Okay, and in case of this shift register and set reset method, you can directly get access to these flip flops. So, what may happen is that even if this setting up this shift register may take 2n number of times, which is D sequence in case of time frame expansion method. So, number of clock periods required may be very less or less compared to this one in case of time frame expansion method. But you have to remember that in time frame expansion method we get access to the flip flop through combinational circuit, that is to the primary input outputs, primary input. So, it may happen that after 3 or 4 time frequencies you may lead to a case where you may have inconsistency, because whenever you want to set or reset a flip flop directly to the set or reset line, there is no question of inconsistency, because somehow I am going to get control of the set and reset lines by flip flops, the sequential register or scan chain or direct pin outs. But what you are gaining is that we get a direct control to the flip flops and there is never any question of inconsistency. Therefore, that is never you can come to a case that you cannot control the output of this case. If you remember this example, like in this example you say that by using the time frame expansion method you cannot test the circuit, because using the primary input output you cannot control the primary output, but by this D register what you call set reset line you can directly have this, control this and you can test it. In other words, this method, that is direct access to the set and reset lines of the flip flops if you are using. So, what advantage you are gaining is there is no question of any inconsistency, always you can control the flip flop. So, even if you are applying 2n number of patterns to set the set and reset lines, but you are never going to have any inconsistency. So, just apply D algorithm, get the test patterns, control the virtual primary inputs by the set and reset lines, apply the test pattern, you are done. So, it is very simple, but in case of time frame expansion method you require D sequence number of patterns which is less than 2n, but it is very complex in nature, that is you may have what is the case that you may land up to a big problem that in the last time frame before the success you get an inconsistency and again you have to redo. So, that offline complexity is so high that people have slowly moving towards this what you call this time frame expansion method, they are slowly forgetting and they are going for this set reset line business. Now, we will see in set reset line there is another problem, irrespective of this 2n number of what you call the 2n number of patterns to be applied to do that. So, basically also you have to add this extra set of flip flops. So, if there are 10,000 flip flops in the circuit, so another 10,000 will be required to control the set and reset lines. Sorry, double the number, 2n number of flip flops also required. So, if it is 10,000 number of flip flops in the circuit, another 20,000 you have to put in making up this shift register. So, this design is not a very efficient one, because you have to put double n number of flip flops to test the circuit. So, DFT size will be very high. So, that was also not a very widely accepted technique. So, you can see that this is what I was discussing, that how can you test this circuit. So, these people have say 1 0 1 0 they have done, and they have applied the pattern like 1 0 1 0 in 4 clock edges you have done this one. So, this is how you do the testing, that in 4 clock paths you set it, then you apply this 1 1. So, in 4 places 1 there is let us just have a look at in the steps. So, how you do that? So, this is the circuit. So, you require a 1 over here and a 1 over here. So, you require 4 clock pulses, you shift 1 0 1 0. So, it is 1 0 1 0 you shift it, and then your all the set and state people are done. Okay, so now you apply 2n number of patterns to do that in 2n clock. Obviously, this clock will be much faster than this clock. Now, what you have to do? There is another problem over here, not only 2n, so more complexity you are adding. So, now all these lines has to be 0, because now you want to operate this circuit normally, because you want to apply 1 1 and get this D over here. So, again this 4 you have to apply by 4 clock pulses. So, not only 2n, so 2n plus 2n number of clock periods are required to set these flip flops or reset these flip flops are required, and then again you have to make everything 0, set reset 0, so the circuit becomes normal, and then you can apply the pattern to do this plan. So, huge number of extra number of test patterns are required to control the shift register to do the set reset controlling, and that actually is the bottleneck and is killing us. So, this design was also not very popular, and then actually the what you can call the main design achievement of testing, which is called the most important. If you say that what is the most important design in case of testing, I will say it is the scan chain. So, then the scan chain came into picture, which actually solved this problem forever. So, here people have partially solved the problem, that there is only 2 pins, test in and test out, there is one separate clock, that is the only 3 extra pins people require, but now you require 2n plus 2n number of clock periods extra to set and reset this shift registers which are controlling the set and reset lines to get access. But now, but this actually is also taking, if there are 10,000 flip flops, so you are having 10,000 or 2, if that is equal to n, we are saying if there are n flip flops, then 2n number of extra flip flops you have to add, and 2n plus 2n extra clock periods are required to control this, to do this. So, that is a big problem which is came into picture. Then, so this is our block diagram, as I said. So, A, B, C are the input, this is the test in and this is the test out, 2 extra, they are the shift register input, shift register output, primary output, and 2 clock. So, additional pin is 1, 2 and 3. So, in 3 additional pins you can do it, but if there are n flip flops, 2n additional flip flop you add, additional flip flop you require, as well as 2n plus 2n equal to 4n test patterns to control this shift register. So, this is the penalty we have to avoid, and actually this was solved by a person by a test engineer, which we are calling the scan chain, and which we actually solved this nightmare problem forever, and which actually converted this combination circuit to a sequential circuit and solved most of these, I mean, legacy problems like extra number of pin outs for set and reset lines, extra number of flip flops for this and so forth. So, the last problem what was we see is the sequential circuit is a huge number of IOs if you are using direct control, and the last major drawback was total number of flip flops which is required additionally to do that, and also 4n number of patterns to do that, to this control. So, the concept of scan chain as it came, so it motivated from the shift register in the earlier register. So, this one actually, this scan chain actually, this major idea came from this circuit only. Just have a look at it, then I will just say that how scan chain was invented, and you have to just appreciate the fact that good designs are always very simple. So, what was his idea? The person's idea was, you are making a scan chain, you are making a chain with some flip flops, but he felt that why are you making one additional chain here where already 2 flip flops are available over here? Why we cannot make a chain in this way? That is the question he asked, and you have to tell that he was an engineer, but he always asks very simple questions to himself. So, if you are in a VLSI design paradigm as students, so what is our, as engineers we are, so what is our main idea should be that we should always ask very simple questions, and always we should try to solve the problem in a simple way, rather than making it very complex and trying to solve it using in a very roundabout way and thinking that I am a genius. So, there is somewhat a bit difference when you are solving a mathematical problem and solving a VLSI problem. These are some quote unquote thumb rules. Like if you can solve a problem in a simple way, try to solve it in a simple way, because it will require less number of gates, less number of power, less number of test engineers, and if you want to solve it in a very complex way, then it will be looking very nice design, but it will take more power, more area, more design effort. So, that is not appreciable in case of VLSI design. So, the person asks a very simple question, that if I have these shift registers over here, or you are making a register over here, why I cannot make a shift register using the same flip flops? We already some flip flops are available in my circuit. If I can make a chain over using this only, then I go away with the extra headache of this one. That was a simple question he asked, and then he said that can I solve it, and it was solved as we see, and that created the revolution. So he said that I will use the same number of same flip flops which are already available in the circuit to design the chain. That is a shift register chain, and there will be two modes in my circuit. One mode will be test mode, in which case all these flip flops will become the chain. That is, this mode is there. In this mode we are actually shifting this one to control it. So he said that in my case this one will become my shift register, and this circuit will not operate normally. And in the second phase, when your this thing is all of them you are making 0, so then these flip flops will be not in a chain will not be there, and it will start operating in the normal way. So that was his idea. Can we do that? So he actually solved the problem in a very simple way, as we will see. So in the test mode, what is the idea? In the test mode, all the flip flops are decoupled from the circuit and they are connected in a shift register, that is called the scan chain. Okay, and when the circuit is behaving normally, the flip flops are removed from the chain and connected back to the circuit. So there is two ways. In one way, your flip flops will be chained and this combination part of the decoupled, and another when the circuit is in a normal mode, this chain will be decoupled and the circuit will be in a normal mode as a flip flop. Let us see how it is done, and if it is doable, then the problem is solved. So what he said is that he considered that I will have a very special kind of a flip flop, same flip flop, but instead he will put a multiplexer in before this. Only that is the only thing he required to make this whole problem solvable. So with each flip flop, now he is adding a simple multiplexer. So in the multiplexer he is saying that let us say that this is your circuit. Okay, so you can think that this is a normal input from the next state function block. So you can have this idea is that, so there are some flip flops, you can have some AND gate input. So you can also think this is another AND gate, these are connected and so forth. Okay, here you can say that there is an inverter like this. This is A, B, C and D. This is some of the inputs he is saying. Okay, and this is your outputs, you can say. Okay, so you can also say that this is also same input. See, this is actually feedback here. That also you can assume. You can assume anything. Okay, so these are the connections. Now what he has said is that now just before, so if you forget about the multiplexers, the connections will be something like this. The connections will be something like this, because how the next state function block means there will be some combinational circuit, primary inputs will be there and they will be connecting to the inputs of the flip flops. Now what he said that instead of doing it, what he has done, he has just put 1 multiplexers. He has decoupled this. The output from this combination cloud is now connected via 1 multiplexer. Now he said that I will have a mode. So these mode are the common circuits. And what are the input of the multiplexers? One input is the normal, which is coming from the combinational part of the NSF block, and the other input is, if the first one is an additional input, that is called the scan in, which is the input of the shift register. And for the second multiplexer, what you will do, one input is coming from directly from the combination circuit, the normal mode, and the other is the output of the last flip flop in the chain, this way. Similarly for this one, what you are going to do, one input is directly coming from the NSF block, that is the combination circuit. Other input is actually coming from the output of the second last flip flop kind of a thing. Now what he is doing, so this is what is the arrangement. Now what he is doing, so when you are saying that, so this is the arrangement of the circuit he has done. Okay, and he said that this is solved my problem. So how it is solving the problem, we'll see. So this is actually following a scan chain. So what additionally he has done, he has taken a flip flop. So say this was the D and Q. So this was the connection. So he said that just eliminate this for the time being. So what was coming, you just, that was same thing, just put a multiplexer over here. You say that in case of 0, this will be the connection, but in the other case 1, I will have my own input and this is the control line. So if the control is 0, then normal input what was flowing is fine, but if it is 1, then I will send my input, the first flip flop. In case of second flip flop, it will be this output of this one. This one is the output is going to be. So if I make mode is 0, then it is normal connection, whatever in the circuit. But if I make it mode 1, then I will take control of this chain. So let us see how it is done. So this is the additional thing I was talking about. So this is your flip flop. Before that he has put one multiplexer. So this is his control for the first flip flop, normal output for this one, and this is the mode. So this is actually you can call this block diagram of a scan flip flop. Now so nowadays flip flops such as scan flip flops. Here we will have normal input, scan in, that is special input, this is scan out, clock and mode. So if your mode is equal to 0, the normal input will be flowing in. If you have mode equal to 1, then the scan in will be feeding in, and that is the two cases. So this is our scan chain loop, normal input, scan input, clock and the output. Output is common. This is the block diagram of this one. Now you see what he has done. So now he said that I want to take control of the whole flip flop. Okay, so as I told you, so you may have some inputs like this. This is an inverter, if you remember. So this one was our inverter. So there was some AND gates over here. There was also some AND gates over here. this was a short, this was C, this is connected from here. So, now he says that for some testing you assume that for some testing also you assume that this C has to be a 1, this one has to be a 1. For some fault you require that this has to be a 1, that is this output, because this C is feedback over here. So, you require this to be a 1. So, for some reason you want that, okay. And other things, this input A, this input B, this is C and this is D. So, you can call that this D is also connected to this one as this one, same case, and you say that I require this to be a 0 for some fault testing, just assume that is fault sum testing. So, how you will do? So, what you require in this scan chain? So, what you require in the flip flops, this output you do not require, C you require to be 1 because this is a virtual primary input or secondary input, that has to be made 1. So, you require controllability of this, and this also you want to make it to be a 0, okay, because this is connected to this pin which has to be a 0. So, how to do that? So, if you look at the old story, that is control reset. So, what you have to do? You have to make this set equal to 0, reset equal to 1, reset equal to 1. So, this will be 0, this is 1. So, set will be 1, reset will be 0, and here it is don't care because you don't care about this. So, once this is done, so you will get 0, 1 and required, then you have to make set equal to 0, reset equal to 0, this equal to 0, this equal to 0, then the circuit will be normal mode and you can do that. So, but for that, if we see that if there are 6 flops, so what do you require? So, 6 flops you require either 3 flip flops, so either you require 6 pin outs. So, you require either 1, 2, 3, 4, 5, 6 extra pin outs, 6 extra pin outs you require, or whether what you know, or whether you have to use a shift register which will having 6 flip flop, and that makes your life very hell, because either extra number of pins or extra number of what you can call flip flops. So, what this person has done, he has put some extra multiplexers. Now, he is saying that already these 3 flip flops are there in my circuit, then why do you want to additionally incorporate another flip flop chain to do that? So, he said that when you have to get the value of say 1 over here and a 0 over here, that was required. So, this was D over here. So, he wants to do that. So, why you should use another extra chain? So, he said that I will make my mode equal to 1. So, when mode equal to 1, so this input get connected to here. Okay, this output get connected to here, because this normal output from the NSF block is now cut, because all the modes are 1, these are flip flop. So, this is connected to this one. So, now you see automatically a chain has been developed. Using this is very important to observe that a chain has been developed not by using any extra flip flops. Again I repeat, not by using any extra flip flops. It has been obtained by using the flip flops which are already developed, already was there in the circuit, by additionally adding some extra marks. That is the only thing he has added. So, now you make mode equal to 1, so you get the chain connected. Now, what you have to apply? So, you have to apply 0, 1, x, and you have to apply 3 clock pulses. So, that's why I told you that has not been yet solved, all that part is not yet solved in a very matured way, that how can you reduce the number of clock periods to do the testing. So, in this case 3 flip flops have to be controlled. So, you apply 0, 1, x, and then you apply 3 clock pulses. So, initially the 0 will be x will be here, this will be x will be here, x will be here, then you apply a 1. So, you will get a 1 over here, x and x over here, then you apply another clock pulse kind of a thing. So, you get the chain set. So, a chain can be easily set over using some patterns. So, that we will again see some explicit examples, but in 3 clock pulses you can set it. Now, what do you do? So, it is 1, this is sorry, it is 0, this is 1, and this is x you require. Now, what do you do? So, now again you know that, so some inverter is there, some AND gate is there, something like this. Now, you want to test your circuit by applying some patterns. So, now what you have to do? So, now again you have to decouple this chain and make the circuit in a normal mode, that is set reset both has to be made 1. So, what you can do? You just make this mode equal to 0. So, once the mode equal to 0 will be there, the normal circuit input will be going to the outputs of the inputs of the flip flops. So, make mode equal to 1 and normal connection is there, flip flop already set, you can do it. So, here what we have achieved. So, this is actually just in a block diagram, we will see what is there. So, this is what is required. So, you can see that this is the secondary outputs, this is the secondary inputs, this we have to virtually control. So, what this person has done? So, he has done mode equal to 0. If mode equal to 0, the secondary inputs are directly coming to the circuit. Okay, in this case there is nothing controllable, the circuit is operating normally. Now, see what you are doing. So, in this case you are making, if mode is you make as 1, then what happens? You can get directly control of these flip flops. You can control them, set whatever value you require you want, and then you come back and make mode equal to 0, then this scan chain will be decoupled, there will be no chain, the normal circuit will be there, you can apply your test pattern and do the testing. Okay. So, this was about the lecture about scan chain. So, next lecture we will give some elaborate examples and what is the advantage and what is the disadvantage and so forth. But before closing, we will just see one thing, that what is the gain we have achieved. So, gain we have achieved is, now if there are n flip flops in the circuit, we do not require 2n number of flip flops, we do not require 4n number of clocks and patterns. Okay, so what we require, if there are n flip flops, we require n marks, and it is only 2:1 marks, whose size or area is much less than the number of our flop. So, you just require n flip flop, n marks is required, and you require n patterns to set the flip flops. So, in last case we require 4n, now we require only n, and instead of 2n extra flip flops we require just n number of marks. So, we have reduced the problem a great deal, and that actually became the path opening for testing of sequential circuit. So, if you say what is the best design which is possible has been reported in case of sequential circuit, from my opinion I will be saying that is the scan chain. So, now so it has solved a lot of important problems it has solved, like time frame expansion, collisions or inconsistencies it has solved. Secondly, what it has solved? Secondly, it has solved about you do not require extra flip flop, just you require n marxes whose multiplexers 2:1, whose size is much lower than flip flop. Secondly, you do not require 4n number of clock periods to set or reset, you just require n number of patterns to set or reset the flip flops. And also you have to observe one thing, that here flip flops do not require a set and a reset line, it is not required over here, you are doing it in the normal way. So, now the flip flop size can also be made smaller than the set reset flip flops, so that you can incorporate this one inside. That is, you can say that if I have a flip flop with set and reset signals, then area will be larger than a circuit than a flip flop which does not have a set and reset line. Okay, then you can think that the marks area, you can say the flip flop with set reset line is almost equivalent to a flip flop with a marks. So, in fact, this additional marks is not at all a problem. So, additional marks we are adding, that n marks area we are also saving by not using any kind of a set reset flip flop. So, that is again another very great boon we are getting, correct. And only thing is that n number of patterns will be required to do this. That is one only problem that still remains and cannot be solved as of now we are seeing. And one more thing is that in case of scan chain, okay, so this same flip flop, you can see that the same clock is there, but now the clock is operating in two different modes, that you have to know. This is a bit complex concept, because when the circuit is operating in the normal mode, that is in this mode, if you can see the circuit is operating in the normal mode. So, if this normal mode is there, then the output of this flip flops will go to this combination, lot of combinational clouds will be there, and then again you can get the output. So, there is a delay, but so your clock has to be bit lower in this case. But when you are working in a scan mode, then what is happening? This output, this is your chain, this output is no longer there. So, your flip flops are only in this mode. So, there is no combinational delay. So, you can use this clock in a very fast rate. So, when you are scanning in the data to set the values in the flip flops, you can do it in a very fast rate, because there is no combinational delay that much. But when you are operating the circuit in the normal mode, so you have to do it in a bit slower rate, so that this combinational delay are matched. So, almost all the problems have been solved by this scan chain. Only one problem that remains is that if the n number of flip flops, in the worst case n number of patterns are required, or n number of bits 0s and 1s are required to control the flip flops to 0 and 1. So, that is what is only the problem that remains to be solved. So, in the next lecture on this, what we are going to see, we are going to see how we can handle this n clock period business, how can you reduce it, this is one more, and second we can see that what are the other variations or other advantages we get in scan chain. Okay, with that we close for the day. Thank you.